This is the second module of the course on environmental geography. This module is on Earth systems based on Chapter 2 of your book. And I am Nathan Bowden, your lecturer for this module. In the first module, you were first introduced to the different spheres. They were the Geosphere, the Hydrosphere, the Atmosphere, and lastly the Biosphere. In this lecture, we will go into more details on these four spheres and where they came from. The origin of this Geosphere is basically the birth of our planet from an immense cloud of gas and interstellar debris called a nebula, shown here in the picture. The Geosphere, what is it? It is solid Earth with its deep molten portions. Is it a static or non-moving mass? No, it's not. It's dynamic. It's not non-moving. It has a constant energy transfer that build mountain chains, ocean basins, and such hazards as volcanoes and earthquakes. It also provides many benefits such as mineral wealth and energy resources. The origin of the Geosphere is approximately 4.5 billion years before present. An immense cloud of gas and interstellar debris, which we call a nebula, began to collapse under its own gravity. Most stars, like our Sun, are born in clouds of gas and dust called nebulae. The solar system was formed along with the Sun when part of a nebular cloud became dense enough to collapse. And there we see in the far right of this sheet a diagram of the collapsing of the nebulae and them becoming more denser objects such as the Sun and the planets. The densest and the hottest center of this nebulae became the Sun. The dust, rocks, and gases swirling around the Sun coalesced to form our solar system, which we call planets. The rocky planets are the closest to the Sun: Mercury, Venus, Earth, and Mars. The large gaseous planets are further away: Jupiter, Saturn, Uranus, and Neptune. Maybe some of you noticed that Pluto is not one of the planets. It is no longer considered a planet, but a planetoid. It's too small and too far away from the Sun to be considered a planet anymore. Here we have the planets in order. Again, the rocky planets Mercury, Venus, Earth, and Mars are the closest to the Sun, and the gaseous planets, the giants, the gas giants, starting with Jupiter, Saturn, and then going on to Uranus and Neptune, are here in alignment. However, you must not think that this is drawn to scale. The planets are much further apart than shown in this figure. The early Earth was an aggregation of nebular debris, of many collisions of different sized particles, various sized particles. The heat generated by the debris collisions through gravitational compression and by decay of radioactive elements such as uranium, thallium, and potassium. Early Earth fairly uniform compositionally and also partially molten. Earth's moon, it is suggested that probably after the early Earth was formed, a piece of the Earth was impacted by a large body, approximately the size of Mars, which ejected a part of the Earth. This is called ejecta. This ejecta flung out from the Earth and was returned into the Moon. The moonscape, or the Moon as it's seen today, is not unlike the early Earth. So you see many impact craters, and on the far side, The oldest surface of the Moon is preserved from old impact structures, possibly from 4 to 4.5 billion years ago. On our planet, the planet Earth, it's quite rare to find impacts of craters. This one that you see the photo of is in Arizona. This crater is 1.2 kilometers across, and it's in a desert. And this is formed by an asteroid of approximately 20 meters, which struck the Earth around 50,000 years ago. Question is why? The geosphere changes through time. We'll be looking at plate tectonics in further detail. So the surface of the Earth is constantly being renewed. This is in contrast to the Moon, which is not being renewed. Now let's look at the compositional structure of the geosphere. The Earth began to differentiate into layers with varying compositions. The denser elements, such as iron and nickel, migrated to the center of the planet. Less dense elements like silicon, aluminum, oxygen, potassium, and sodium floated to the surface. Once all the elements moved and the Earth was differentiated, there were 3 distinct layers which it resulted in. The innermost core, outside of that is the mantle, and lastly the crust, which consists also of the surface of our planet. The Earth's core has 2 parts. The first is a solid inner core, approximately 1,200 kilometers thick. It is approximately 1.7% of Earth's mass, and it is a composition of an alloy of iron and nickel. The liquid outer core is the next 2,250 kilometers, and it's approximately 30.8% of the Earth's mass. Again, the composition is iron with some nickel, but has up to 10% of other light elements, such as oxygen or sulfur. The composition of the core has only been inferred from studies. We've never reached into the core of our planet Earth, so we haven't measured this directly. But through studies on the density of our planet and the composition of our iron-rich meteorites, which go back to the early essence of the nebula and other planetary cores, lets us derive the composition of the Earth's core. The mantle, which is in between the core and the crust on which we are walking on, the mantle is the majority of Earth's interior. It is 2,850 kilometers thick. That's roughly 2/3 or 67.1% of Earth's total mass. The composition is variable, but mostly homogeneous, with mostly magnesium, and now decreasing abundance of what was so abundant in the core, silicon, oxygen, and iron. Compositionally, again, we have never reached the mantle. We have derived this percentage and these and the abundance of the mantle through studies on the Earth's density, also through meteorites, the way that seismic waves go through the planet Earth. They all lead to us the basic idea of Earth's mantle composition. The Earth's crust. The Earth's crust is the outer thin layer of the Earth. It's approximately 80 kilometers thick at its deepest point, and it contains rocks that can be examined at Earth's surface. So here we have direct contact with the geosphere. There are 2 different types of crust. We have the continental crust, the land part, which is 30 to 40 kilometers thick, composed mostly of granite, and the oceanic crust, which is anywhere from 5 to 8 kilometers thick, and this is basalt. The origins of the atmosphere. Part of the nebular cloud, which formed the geosphere, also had gases inside of it. Some of these gases we know were hydrogen, helium, methane, and ammonia. This we see as Earth's first atmosphere, and it almost certainly included these gases directly from the nebula. Prior to Earth's complete differentiation in the geosphere, that is to say before it was differentiated into the core, mantle, and crust, it was very hot, and the liquid outer core was fully developed before the complete aggregation. So these gases could not condense yet to form later or be our oceans. So it's still quite hot at this time and liquid. The second atmosphere, the secondary atmosphere, was composed of volatiles. These are easily vaporized elements or compounds from the initial solid Earth. These volatile compounds include hydrogen, carbon, and nitrogen, and also compounds formed from these elements, such as water, carbon dioxide, and ammonia. These elements and compounds are characteristics of primitive meteorites, which we've encountered through our history, called carbonaceous chondrites. These are thought to be representative of the nebular cloud composition that condensed to form the solar system. Therefore, materials in the early solid Earth that contained volatile components, if vaporized, could have contributed to the formation of Earth's atmosphere. And now, today's atmosphere, we call it the third atmosphere, its composition we have measured. It's approximately 78% nitrogen, 21% oxygen, between 0 to 4% water and variable gases, and then argon, less than 1%, carbon dioxide is and then trace elements, neon, helium, methane, etc. The formation of the third atmosphere, how did that come about? Today's atmosphere, as I mentioned, is called Earth's third atmosphere. Big changes were needed to transfer Earth's second atmosphere to make it into the third atmosphere. Large volumes of water and CO2 had to be removed, and a lot of nitrogen and oxygen needed to be added to evolve into the third atmosphere. How did this come about? Well, the excess H2O went into the hydrosphere. As the Earth cooled, the water condensed and became liquid. That was by approximately 3.5 billion years before present. It was when the Earth's oceans formed and precipitated, and the geosphere began to cool. Another point I would like to add, that the biosphere began to develop approximately 2 billion years ago, and at this time microorganisms transformed some of the other gases, CO2 and methane, into oxygen. Compositional structure of the atmosphere can be divided into several stratifications, as you see in this picture on the left. The closest to Earth is the troposphere, followed by the stratosphere, which encompasses also the ozone layer, where we find the ozone layer. Above the stratosphere is the mesosphere, and these three together, the troposphere, the stratosphere, and the mesosphere, compose what we call the homosphere. And then above the homosphere is the heterosphere, which is another word for the thermosphere. The thermosphere is also the place where the aurora borealis is formed. In total, the atmosphere's overall thickness is about 480 kilometers, more or less. We cannot say for sure, because at different parts on the planet the thickness is different. And the atmosphere, as I mentioned, has two defined compositional variations, the homosphere and the heterosphere. Temperature structure of the atmosphere. Solar radiation interacts with the Earth's surface, of course, and produced these four atmospheric layers I mentioned. And I will go into more detail. These four layers, in ascending order, are the troposphere, stratosphere, mesosphere, and thermosphere. the troposphere. The troposphere varies in thickness to about 7 km near the poles and 17 km near the equator. The change of temperature in the troposphere is related to the heating of Earth's surface by solar radiation, which means the sun's rays reach the surface of the planet and heat up the Earth. At this part of the troposphere, on the closest to the Earth, it's warm. But as you go upward through the troposphere, you see decrease in the temperature, and the troposphere ends at a place called the tropopause. The troposphere is the most dynamic place within the atmosphere because of the winds associated with it. Highly significant, of course, is where most life and also where weather occurs on our planet. About half of the mass of the atmosphere, that's correct, gases do have a mass, so half of the mass of the atmosphere is in the lower 50 kilometers of the troposphere. The stratosphere is above the troposphere. Here, the temperatures increase as you go up through the stratosphere. The higher temperatures of the stratosphere versus the underlying troposphere come from the rising and crossing of the boundary zone of the tropopause. The top of the stratosphere is marked by a temperature decrease, and this boundary is called the stratopause at an altitude of approximately 50 km from Earth's surface. The stratosphere characteristics: the upward temperature through the stratosphere prevents air from rising within it, and it causes it to be internally stratified, which means it has its own layers. Small quantities of water vapor and stratified character of the stratosphere make it a generally cloudless part of the atmosphere, so the winds are parallel to the Earth's surface. It's observable as clear area above clouds in the troposphere. The Mesosphere. Above the stratosphere, so from approximately 50 to 80 kilometers in altitude behind the Mesosphere, here the temperatures again decrease upward through the Mesosphere to a boundary zone, again the mesopause, where the lowest temperatures in the atmosphere are present. Temperatures decrease going through the Mesosphere, going upwards, because they reflect less concentration of gas molecules that absorb UV radiation. The gas molecules having a mass tend to go downward, and so at this part of the atmosphere, the mesosphere, there are less gas molecules to absorb the UV radiation. And this continues as you go upward through the mesosphere. It's also related to presence of small amounts of CO2, which CO2 absorbs and re-radiates the solar energy. But again, there are so few other gas molecules to absorb this energy, it's often lost to space. It cools the mesosphere. So this is the opposite of the effect CO2 has in the troposphere. In the troposphere, CO2 acts as a greenhouse gas by trapping heat, energy from Earth's surface, and transferring it to the gas molecules in the atmosphere. The mesosphere, although the concentration of gas molecules is quite low, there is still enough of them to have some significant effect. So there's friction within the few gas molecules that are present, causing such things as meteoroids to heat up. These we call shooting stars, and most of the meteoroids that collide with our atmosphere are burnt up in the mesosphere and don't reach the surface of our planet. The exosphere, which is beyond the mesosphere, where the satellites travel, is the atmosphere-space boundary. The thermosphere, the outermost atmospheric layer, is the thermosphere. Here, the temperatures increase as the number of air molecules decrease. The thermosphere goes up to approximately 480 kilometers. Compositionally, it's defined as the hydrosphere. The temperature increases upward due to interaction of intense solar radiation with increasing sparse gas molecules, which are mostly nitrogen and oxygen. As mentioned before, The aurora borealis, also known as the northern lights, are formed in the thermosphere. It's where the solar radiation is quite intense, and it changes the gas molecules into their more charged particles, also called ions. Because of this ionization is happening in the ionosphere, the northern lights are created. These charged particles collide with each other, and they form the aurora borealis, called the northern lights, in the North Pole, or the aurora australis, the southern lights, over the South Pole. And these are seen on the surface as moving sheets and wisps of colored light, visible at high latitudes on very clear nights. Earth's hydrosphere, directly connected between the solar energy and Earth system's processes, consists of all water and oceans, on land in streams and lakes, and in glaciers and other accumulations of ice in the atmosphere and underground. The water planet, which we also call the Earth, it's a nickname we've given our planet. Water covers, the hydrosphere covers approximately 71% of Earth's surface. And the Earth is uniquely positioned in the solar system so that water exists in all three phases: solid, we call ice, liquid, and gas, water vapor. The origin of Earth's water. How did the Earth become so dominated by water, you may ask? Well, water was part of the original nebular debris that was coalesced, which formed the Earth. Other contributors may be volcanoes, which are releasing the volatile gases, as I mentioned, in the Earth's second atmosphere. So it released more water vapor, and possibly, of course, comets and asteroids coming in and slamming into the Earth. Upon Earth's more complete cooling, as the Earth cooled down, the water vapor condensed and precipitated as liquid on the Earth's surface. The oldest known rocks that formed from the ocean sediments are approximately 3.8 billion years old. These are confirmed some compositional characteristics of the second atmosphere. So the hydrosphere on our planet Earth is approximately 3.8 billion years old. The hydrosphere, if you see 100% of the hydrosphere, 97.2% is ocean water, salt water, and only 2.8% is fresh water. You see this in the figure on the right. And of this 2.8 fresh water, 68.6% is ice, 30.1% is underground water, and only 1.3% of all fresh water is on the surface. So unlike the atmosphere or the geosphere, the hydrosphere lacks an internal structure, but does possess distinctive reservoirs. The world's oceans are the largest reservoir of hydrosphere at 97%. So 1.3% of 2.8% means that the available fresh liquid surface water that we are able to use is only 0.036% of the hydrosphere. Only that small amount is available to us. There are different reservoirs. As I mentioned, 2.8% is fresh water. These fresh waters are in lakes, streams, rivers, are underground, and also in the atmosphere, and accumulate in glaciers, ice caps, and ice sheets. The oceans, or 97.2% of all the water, is on the ocean, which covers 71% of the Earth's surface, as I mentioned before. And in some areas, the ocean is 3 kilometers deep. The deepest being the Mariana Trench and the Pacific Ocean. The internal structure is defined by variations in salinity of the oceans and temperature. But as one big reservoir, it has only two parts. The upper layer, approximately 200 meters thick, is warmed by the sun and mixed by the waves and currents. Here you see in the figure on this of this sheet, the movement of water in the world ocean, the currents. The lower layer has a depth of approximately 1,000 meters. The solar radiation has little to no effect. The water temperatures are very low and range between 0 to 4%, just below freezing. Water can still be in motion because of salinity and temperature differences that change water's density. So the denser, colder and saltier water sinks and slowly flows to the deep ocean back to the surface in a global circulation, which I mentioned in this figure. The world ocean is a major influence on global climate. Why? Because water has a great specific heat capacity compared to compared to air in the atmosphere. And what this means is that water can absorb large amounts of solar radiation and before it transfers it within the bonds between the hydrogen and oxygen molecules. Glaciers, ice caps, and ice sheets, another reservoir of fresh water on our planet. These glaciers are formed when the snow accumulation is greater than the melting of the snow. Seasonal conditions affect the glaciers at higher elevations, and there are large glaciers on the north and south poles. But you also have mountain or alpine glaciers, which vary from small patches to large rivers of ice that slowly form a flow downslope. And these slowly flowing downslope glaciers form many of the landforms of the geosphere. Where these glaciers coalesce and they cover a very large area, we call these ice caps, less than 50,000 square kilometers, and ice sheets. And an ice sheet is greater than 50,000 square kilometers. In our modern era, ice covers about 10% of Earth's land area, most in ice sheets on Greenland and one on Antarctica. The water cycle. The hydrosphere interacts with other Earth systems in the water cycle, transfer prized resources among its reservoirs, such as the oceans, atmosphere, and on underland. The atmosphere of the ocean is a key of the water cycle. It's approximately 86% of the water vapor obtained through evaporation from the seas. When this air rises, it cools, causing water vapor to turn into tiny droplets, which form the clouds. Where air temperature falls, as when air rises along mountains, the liquid water droplets condense and fall to Earth's surface. This precipitation we see as rain, snow, or hail. Precipitation is the transfer of water to three reservoirs on land: ice, surface water, and groundwater. Rivers and streams carry water back to the oceans, completing the cycle. Water is used, of course, by plants, animals, and people, which are the biosphere. But this is only a temporary reservoir, and again, they will also eventually cycle back into the atmosphere through respiration and transpiration. Water cycle is the Earth system processes and interactions in the water to involve energy and matter transfer between these three other spheres: the atmosphere, the biosphere, and the geosphere. Lastly, the last biosphere that we'll be talking about consists of all life on Earth, the biosphere, and of course all life from the largest on our planet has ever seen, the blue whale, to the smallest bacteria. On a molecular level, this is a very complex and vast ecosystem. It produces food, has a very large role in the carbon cycle, acts as a pollution filter, capture of energy, and of course aids in soil development, and of course also atmosphere development. As I mentioned before, oxygen on our planet is now 21% due to the molecular transfer of microorganisms. So what started evolution to make life so diverse? Well, we have gone through chemical and fossil or paleontological evidence in ancient rocks, which provides insight in the origin of life on Earth. And we look at these fossils, the fossil record, to study the evolution on our planet. Example of fossils will be in the next sheet. These fossils can be actual remains, the ossified fossils, the stone turned bones of creatures or their shells, or they can just be imprints of the organism, such as such as their footprints. So here we see some of the fossilized remains of former organisms. In photo A, you see an ammonite, which is a member of a group of shelled animals related to modern squid and octopi, approximately 350 million years ago. And B, these are the fossilized remains of a relative of the Tyrannosaurus rex, a dinosaur in this group which lived approximately 170 to 65 million years ago. And in photo C, you see fossilized evidence of seed plants as they grew, left their impressions in Europe and North America, approximately 280 to 300 million years ago. Thank you for your attention on this module. Please continue with your quizzes and assignments, and when you finish that, move on to the next module.